Hello and welcome to week 4. I hope you enjoyed the last 3 weeks. We covered during them fundamental material and tools that will serve you well for the purpose of this course and beyond. As I mentioned earlier, do not get discouraged if not everything is crystal clear at this point. If you're comfortable with the homework problems, then you are in good shape and you'll be able to apply these tools to real-life problems in your work or school environments. This week, similarly to the last 2 weeks, we'll cover a tool, you might call it so, which is needed almost always when we deal with the processing of videos. The tool consists of techniques of estimating the motion in a video of a dynamic scene. In other words, in finding how each and every pixel in the scene has moved over time. This is a fundamental step in a number of applications, like for example tracking. This is the problem of following an object over time, like a player, let's say, in a basketball game, something which is done automatically by us humans, but it is a rather challenging task for the computer. Or human-computer interaction, that is, interacting with the computer not with the traditional mouse and click anymore, but by assuming that the computer, or say a robot, has eyes that can see us and understand, for example, our motions and our actions. As we will see when we cover in detail video compression in a few weeks, motion estimation is an integral part of any video compression algorithm or standard. We'll talk primarily about the so-called direct methods for estimating motion, that is, phase correlation, block matching, and spatiotemporal gradient techniques. We will also talk about color. We will cover some of the basic information about it. We'll describe some spaces for representing color, and we will also discuss some basic considerations when we process color images and videos. In this first segment, we will distinguish between 3D and 2D motion, and also between true motion and optical flow. We will then provide some examples of the application of motion. We will be encountering motion in different parts of this course, especially when we talk about video compression. So, let us proceed with this material and enjoy week 4. The world we live in is three-dimensional. I therefore need the three-dimensional axis system, an X, Y, Z system as shown here, to describe the motion of objects or their trajectories in this three-dimensional world. So what we see here is this ball at times t, t plus 1, t plus 2, t plus 3, and so on. Now, if I only have available one camera as shown here, when we talk about monocular vision, all I am able to acquire is the projection of this three-dimensional motion onto the two-dimensional plane, let's call it XY plane. If the camera is not calibrated, I'm not able to correspond, for example, sizes from the image plane to the world. So if, for example, this diameter of the ball is 20 pixels here on the image, I do not know what the size of the ball in the real world is equal to, how many centimeters, for example, this diameter is. Similarly, we see that intentionally, at time t plus 1, here the ball is smaller than the ball at times t on the image plane, and this is because the depth, the distance of the ball from the image plane has changed. So, although I'm interested in estimating the motion of objects in the three-dimensional world, all I'm able to do with one camera is estimate the motion of the objects in the two-dimensional world. Again, if a calibrated camera were available and I also knew the geometry of the scene, then I would be able to go from the 2D motion to the 3D motion. Similarly, if 2 or more cameras were available, I would be able to find the depth in the scene within a scale factor, and so on. However, for the better part of the course, we'll only deal with one camera as shown here, and therefore we'll deal with the estimation of the two-dimensional motion. So the basic form of the motion estimation problem is depicted here. Given 2 or more frames, I'm interested in finding out how an object such as this one moved from one frame to the next. So from frame K minus 1 to frame K, and how it moved from frame K to frame K plus 1. Similarly, I might define a region, such as this one, and be interested in finding out how this region moved from one frame to the next, or I might be interested how a single pixel moved from one frame to the next. And these vectors denote the motion in this two-dimensional plane of this particular object or region or pixel. As far as notation goes, time will be denoted as subscript here, as shown here, or alternatively I can use the notation I, X, Y, T minus 1 to denote the image frame. The intensity is I, coordinates X, Y at T minus 1, and here it becomes X, Y, T, and so on. The definition of the optical flow is the change of the light in the image, or on the retina of the eye, or on the camera sensor, due to a relative motion between the camera and the scene. So in general, by estimating the optical flow in an image, we are obtaining an estimate of the motion in the scene, or as we discussed, the two-dimensional projection of the three-dimensional motion onto the camera. There are, however, two cases that I want to discuss here. One, when the optical flow is zero, although there is motion in the scene, and two, when the optical flow is non-zero, but there is no motion in the scene. The first case, non-zero true motion, but zero optical flow, is demonstrated by this video. This cylindrical water bottle here is rotated on a vertical axis, and since the reflectance properties on the surface of the cylinder are constant, the generated optical flow is zero. You might see actually some displacement of the cylinder here, since I was holding it and rotating it while filming it, and it's rather hard to hold it steady while rotating it. So let me play the video for you. So it is hard to observe any motion since the optical flow is zero. There is no change in the optical flow in the scene. I want to demonstrate the second case by this video, the case of zero true motion and non-zero optical flow. Due to the change in the ambient light, the optical flow is non-zero. If you focus, for example, on this statue or this business card holder. However, nothing moves in the scene. So let me play this video for you. So if the ambient light is constant, we don't have to worry about the second case, and therefore, with the exception of this issue that was described here, the estimation of the optical flow will provide us with a good estimate of the motion in the scene. There are numerous applications in computer vision, video processing, robotics, animation, where motion is estimated and used to perform various tasks. Some examples of such applications are listed here. In object tracking, the objective is to determine the location of an object at any given time instance. In human-computer interaction using visual inputs, the objective is to communicate information to the computer with the use of a camera, capturing the motion of the body, arms, hands of a person, as well as the expression of the person. In temporal interpolation, the objective is to create or estimate missing frames in between existing frames. Video rate up conversion is a primary example in this topic. In removing noise from a sequence, we are interested in using both the spatial neighborhood of a pixel in a frame as well as the temporal neighborhood. In this case, we want to filter along the motion trajectories. Finally, in video compression, we are predicting the values of each and every pixel in the current frame by utilizing their motion as determined from the previous frame or the previous frames. We then encode the predictor parameters, the motion, as well as the prediction error or the displaced frame difference. Clearly, we want to perform as accurate motion estimation as possible. This is indeed the case for the first 4 applications mentioned here. For the video compression application, however, accurate motion estimation is also important, but we can trade accuracy of the motion with reduction in computational complexity or speed of estimating the motion. We can afford this because we are given the chance to correct for the inaccuracies in the motion estimates by encoding the prediction due to motion error or the displaced frame difference. In any case, don't worry if this is not crystal clear right now, since we'll cover video compression in considerable detail in later weeks. We show next some examples of the first 4 applications. Object tracking is a very challenging problem with considerable research and development in academia and industry alike. We use here a MATLAB program to demonstrate the basic idea. The name of the program is typed in this command window. The name is VIP traffic OF_WIN, and this window pops up. If we press play, then we see these 4 individual windows showing up. So the block diagram of the system is shown here. The raw traffic data are input to the system, and the raw data are shown in this window. Actually, they go out this way, and this is the video that is displayed. The frames are 120 by 160, and the frame rate is 15 frames per second. Then the color video is converted to intensity, to grayscale, and based on the grayscale, the optical flow is estimated using a particular algorithm by the name of Horn-Schunck. We're going to talk about optical flow later in this presentation. So these motion vectors, velocity here, are displayed in this window. You can see those yellow motion vectors. Then based on this velocity, thresholding is taking place, and it generates this binary image shown here. So if there is a velocity vector in an area in a pixel, then this is, after the thresholding, shown as white, while the stationary part is shown as black. And finally, based on this segmentation here, a bounding box appears around the objects, and this is really what we are after. We want to know at each time instance the location of the object. So it is a motion-based segmentation of the objects. The segmentation, again, is shown here in this binary image, is not extremely accurate. For example, you see that you have 2 cars here and there are stationary parts in the car while the car is moving as a complete object. So these are errors in the motion-based segmentation. However, as long as the bounding box is correctly identified around the moving object, then our objective has been accomplished. So let me continue playing the video here. You see again in these 4 windows, original video, the motion vector field superimposed on the video, the binary image due to thresholding, the motion field, and finally the bounding box around the moving object. So if I kind of stop it here, you see that there is a bounding box here, a green bounding box around the moving object. So this is a program you can also run on your own and pay closer attention to it. But it clearly demonstrates a rather straightforward approach towards object tracking based on the motion vectors. We show here an example of a vision-based interface system called Visual Panel, which utilizes a panel such as an ordinary piece of paper and a tip pointer, for example, a fingertip, as an intuitive, wireless, and mobile input device. The system can accurately and reliably track the panel and the tip pointer. The panel tracking continuously finds the projective mapping between the panel and the display, which in turn maps the tip position to the corresponding position on the display. By detecting the clicking and dragging actions, the system can perform many tasks, such as controlling a remote large display and simulating a physical keyboard. Users can use their fingers or other tip pointers to issue commands and type text. And in addition, by tracking the three-dimensional position and orientation of the visual panel, the system can also provide three-dimensional information and can therefore serve as a virtual joystick by which one can control three-dimensional virtual objects. So this is another example of how motion can be utilized in developing these human-computer interaction systems. Motion compensated temporal interpolation is another problem where motion plays an important role. This is the problem encountered in frame up conversion. For example, I want to convert a 24 frame per second movie up to a 30 frame per second video that will be used for broadcasting. So the problem is depicted here. I have the frame at time t1 and the frame at time t2, and I'm interested in generating a frame typically in the middle of these two or at any distance between these two, let's say at time t. One approach towards this temporal interpolation is to duplicate frame t1 into frame t. So in this case, if for example I look at a block such as one shown here, I'm going to reproduce this block at exactly the same location. So if this point here is n1 and 2, then this point here is also n1 and 2. So this is zero order hold. This is of course a very straightforward way to generate the missing frame. However, it can generate jagged motion, because then in going from T to T2 we see that the person here has considerably moved. So another approach which provides, generally speaking, a much smoother motion is based on motion compensation. So I find the motion between this block at frame T and frame T2, and therefore the location now of this block is here at, let's say, n1 prime and 2 prime along the motion trajectory. So then I'll take the intensity of that block and reproduce it here. So this is the basic idea of motion compensated temporal interpolation, and again, by and large, it produces a much smoother motion than the zero order hold. And here in this example, again, the frame we interpolated is in the middle of the two frames. It can be anywhere between the time t1 and t2, and we can have more than one frame, so we can just introduce 2 or 3 new frames between frames t1 and t2. Let us assume we're given 3 noisy frames, and our task is to reduce the noise. We assume that the same type of noise with the same strength, the same variance, was added to all 3 frames. Then if there is no motion among the frames, if the frames, let's say, are identical in that respect, if I take a small region as indicated here and then average it across time, the net effect is that the variance of the noise is reduced by the number of frames I'm averaging. So in this particular case is divided by 3. In videos, of course, of interest, in dynamic videos, there is motion between the frames, but I want to reproduce the same operation, and in doing so I have to be able to find the motion and perform this averaging, this filtering along motion trajectories. So what is that? This is what is shown here in the second row of images. I have tracked the motion, and therefore this block here is not in the same N1 and 2 location, but it moves from frame to frame by following the motion. So then I'm going to average the 3 frames here, the 3 rather blocks shown in red, but they're located in different locations because, again, I'm smoothing along motion trajectories. So this is the simplest possible idea one can perform when dealing with temporal filtering, but the general idea is that I want to be able to find the motion and then perform a type of filtering, spatiotemporal filtering, along the motion trajectories. Clearly the problem becomes more challenging, the motion estimation problem, that is, simply because the data are noisy, and therefore I have to invent robust motion estimation techniques, robust to noise.